research is in the field of theoretical and computational chemistry, and also in the area of astrochemistry. Yeah. So the title of the talk is Explicit, Correlated F12 Composite Schemes for Noncovalent Systems, Interaction Energy and Geometry. So you are
So with this presentation, we have a wide change of topic, and we focus on ground electron state and in particular on non-covalent binary system. And this was a project I carried out during my PhD 2 years ago. So let's start from the very basic. Whenever we run, this is a common graph in computational chemistry calculation, we are far from the exact solution, and we have this error that is called apparent error. And here, of course, we know that this error is divided in the error due to the wave function we are employing for our methods, and the other error is due to the basis set. However, we can try to remove the basis set error and just leave what is called an intrinsic error just due to the methods. How do we remove this error due to the basis set to reach the highest accuracy possible? So we compute what is called the complete basis set limit. So we carry out a series of calculations with different basis sets. Of course, we need a specific family basis set to run in calculation. They have to be hierarchical. And then we use a specific extrapolation formula to estimate our complete basis set limit. However, nowadays, these CBS limits can be estimated much better using those that are called F12 methodology. So they include in a specific form the interactions between electrons. This function allows us to reduce the size of the basis set we have to employ to carry out the CBS limit, and therefore we can employ double and triple beta quality basis set to extrapolate the results that are of the same quality, for example, of a quintuple zeta basis set. So usually, however, if we want to push the accuracy of our calculations, what we do is to start from what is called the gold standard, so CCSD parentheses T method, extrapolate this method to the complete basis set limit, sum to this term the covalence correlation, of course the vibrational contribution, and then we have the contribution of full triple excitation, full quadruple excitation, and going on relativistic effects and the adiabatic Bohm-Oppenheimer correction. However, what we are really interested in, especially in non-covalent system, are the first two terms. So complete basis set limit and covalence correlation. And we can easily include that in an effective manner using this scheme that was presented in the literature. So it's called the CHIP scheme, and it's the sum of three terms. First of all, we compute the energy using the CCSD parentheses T method with the triple zeta basis set, using for approximation. And then we run two calculations with the MP2 method to triple and quadruple zeta basis set, and we extrapolate the MP2 method to the complete basis set limit. And this is much cheaper than extrapolating the CCSD parentheses T method, but very effective. And then we add the last term, which is the covalence method, using still the MP2 method and doing the difference between a null electron and a fusion core calculation with a triple zeta basis set. What about if we want to move this scheme and the other one that is present in the literature indicated as CBS placebo, but using F12 method? We need to account for several things. For example, how do we extrapolate F12 methodology? For the other methods, we have established the n to the -3 formula or the n to the or the 2-point formula. However, for F12 methods, we do not have really a specific extrapolation formula. And in this case, we want to understand which is the best extrapolation formula for these two methodologies. In the case of the CBS placebo, we run more or less the same computation, just we extrapolate the CCSD parentheses T energy using the triple and quadruple zeta basis set, and we do not pass through MP2. we need to understand which is the appropriate basic set, and in particular, we will also focus on specifically developed F12 basic set, and then the formula used for F12 methodology, which theoretically should extrapolate as n to the -7. Why we choose noncovalent complexes? Because they are quite a tricky system, and in particular here we refer to what is the interaction energy, which is defined as the energy of complex AB minus the energy of minus the sum of the energy of the two fragments. This is not a real measurable quantity, but it's very useful from the computational point of view, because we don't need to account for counterclockwise correction and so on, which is usually done via the deformation term, which then leads to the dissociation energy at the equilibrium, and then with the 0-point energy correction, we arrive to the real dissociation energy of a system. We test this the scheme and the CBS plus CBU with the F12 methodology, using as reference is a set of noncovalent complexes, which was reported in the literature, and it's a part of a larger data set, which is called A24, we call this A14. And our target accuracy has to be around 1% with respect to the accurate data reported in the reference. So let's start to understand how we compare our CBS limit with respect to the CBS limit of the reference data. And so here we are extrapolating CCFD parenthesis T F12 energies. And we are employing just two extrapolation, n to the -3 and n to the -5, as others were not very reliable. So we employed a combination of double and triple zeta F12 basic set, and we see that the n to the -3 formula is performing better. If we move to triple and quadruple zeta F12 basic set, the n to the -5 is performing better this time with respect to the -3, and we have an error of 0.77%, so below our target. And then if we employ this partially augmented basic set, we still have a good result with the n to the -3 extrapolation formula. And then we focus on also another partially augmented basic set, which is very similar to the triple and quadruple zeta F12 in size of basis set, and we have an error of 0.76. As we see, for 3 out of 4 extrapolation, we have better result with the n to the -5. So we can say that if we employ the CCFD parenthesis T F12 method, we can extrapolate with the n to the -5. Then, if we focus on our cheat scheme, we have the same two extrapolation, we have the same basic set, and we see that the error with double and triple zeta F12 are much larger. And this time we are extrapolating the MP2 energy, and we sum the MP2 F12 energy, and we sum it to the CCFD parenthesis T F12. And in this case, this extrapolation does not work properly with the double and triple zeta F12 basic set. However, we have very low error and very consistent for triple and quadruple zeta F12 basic set, and very low error with respect to the reference. And then we have again an increase of the error with the May, and we have comparable, and again, the lowest error observed for the June triple and quadruple zeta basic set. And the error is to n to the using n to the -3 is always lower, except for the it's always lower. If we compare the two previous slides very rapidly, we see that in both cases, the lowest error is obtained with the June triple and quadruple zeta basic set. So we say that for us, this is our basis of choice. However, the result with the triple and quadruple zeta F12 are very similar. For the double and triple zeta F12, which is usually the combination of basic sets employed in the literature, we see that the results are good, but we need to use the n to the -3 formula for the CCSD parenthesis T F12 method to have comparable results. To this extrapolation, we need to add the correlation term, and in this case, we see that the chip scheme with the June triple zeta and quadrupole provides again the lowest error of 0.78, and therefore we stick to the June family of value 10. At this point, having understood how to extrapolate the energy for this non-covalent system, we need to understand how we can compute the geometries for this non-covalent system using the same composite scheme. We have tested several geometries and not illustrated the geometries for all systems. So I take the water dimer as test case, and we can focus on intramolecular distances, so the H-O bond within the same molecule, and these bonds are very similar among all the computational approaches that we tested, and the differences are of a few milliangstrom. So this parameter is not very meaningful. Then we can move to intramolecular angles, and so angles within the same molecule. And also in this case, the parameters is not very meaningful. We have changes smaller than 1 degree. So we cannot say based on this parameter, which is the best methodology. And also the other parameter, so the intermolecular angle, is very flexible and cannot be used again to understand which is the best computational approach. So we can rely on intermolecular distances. And in this case, we can see that the scheme based on the CBS plus F12 or CBS or June chip F12 without a F12 method or with the classical on the standard methodology, they have very similar performances, and they are systematically shorter than the reference one. This is because we are including covalence contribution in our geometries, while the reference is not including this term. We have also provided a double hybrid DFT methodologies as reference, which is performing good for some of the complexes. However, we see that what we think are the best approaches in this case is not to compute, to extrapolate the energies, to extrapolate geometries, as is done for the standard correlation methodologies, but we just need to do optimization with a triple zeta basis set and then add the covalence contribution. Summary of this work is reported in this paper with all the other collaborators. And in the paper, we have extended our methodology to larger system, larger in size, and also larger in terms of atoms, so atoms of the third row of the periodic table. And overall, we can say that if we need to understand which is the best composite scheme for the moment, with the F12, of course, the June chip F12 would win. However, it's not comparable with the June chip used for using standard correlation methods, because this method, the one that is placed on the first place, is still cheaper computationally speaking, and we still use it for deriving spectroscopic parameters and thermodynamic estimates and so on. So I would like to thank the group and the collaborators of presenting the paper, and of course all of you for your attention, and the organizing committee for the opportunity to speak.